I'm Vermont Edition co-host Bob Kinzel. Just wanted to let you know that this podcast has been edited for brevity. Thanks for listening.
This is Vermont Edition. I'm Rick Singari, in for Bob Kinzel. In December of 1967, my brother and I woke up to find that the Supreme Gift Giver had brought each of us a Zeroid robot. We hadn't put these on our wish lists, but were these ever cool toys? And they ignited in my imagination the possibility of a world with robots, making that eventuality seem a little more realistic than the Jetsons. But it's more than a half century later, and I'm still wondering, where is my beautiful house with my extremely helpful robot? And when I ask that question, I'm really more concerned about the robot, which begs the more important question, where are we in the world of robotic development? One person who has been doing some serious research in this area is Josh Bongard. He runs UVM's Morphology, Evolution, and Cognition Lab, where his research centers on evolutionary robotics, evolutionary computation, and physical simulation. Josh, welcome back to Vermont Edition.
Thank you very much, Rick. Thanks for having me.
Yeah. So in a global sense, where are we in robot development?
Well, we're actually at an extremely exciting time for robotics. As you mentioned, you received a robot back in the 60s. I received one in the 80s when I was a kid, also from the Supreme Gift Giver. So we've been sort of at a plateau for a long time. It's been difficult to create these helpful robots. But just in the last 3 or 4 years, we've seen a sudden change in our ability to make not just interesting robots or useful robots, but also adaptive robots. So it's an extremely exciting time to be working in robotics and thinking about what we're going to do with them when they arrive.
Okay, where are the great advances? What are they?
So there were two main advances. One of them was a very technical advance in terms of mathematics and figuring out how we can get machines to become increasingly smart. So when we create computer programs, we can sit down and write those computer programs by hand, or we can step back and try and set up a situation in which the machines can think for themselves. So the biggest advance in the last few years was figuring out how to get them to learn for themselves. The second advance is the big data revolution. Everybody's heard of AI, big data. We have all this data flooding in from our cell phones, from our cars, from our buildings, from our roads. And if we feed all of that data to these machines that can now learn, you put those two things together, and we're now starting to see the beginnings of intelligent machines out there in the world with us.
Where are we not keeping up with expectations?
The place where we're not keeping up with expectations is being able to make machines that are autonomous, that think for themselves, but also that are safe. How can we ensure that once machines are out there shoveling the snow, cutting the lawn, and making their own decisions in the real world, how can we make sure that they make the right decisions that we approve of after the fact? That's the tricky part.
Now, Josh, we've been working on robots, not you and I, but humans, since probably around World War II. So why are we not as far along as we could or should be?
So it's taken, as you mentioned, both computers and robotics were invented during the Second World War. And of course, computers have come a very long way since then. But on the flip side, robotics has sort of stumbled along over the decades. The reason why is that we can make machines that are very complicated. Your cell phone is a very complicated machine. We've built the International Space Station. Yeah. These are all very complex machines, millions and millions of moving parts, but they do the same thing over and over again. When we come to robotics, these are machines that exist out in the world with humans, and the world is always changing around them. They always have to constantly adapt. So the Greek philosopher Heraclitus said, "Man never enters the same river twice." Over 2,000 years ago, there was an understanding that one of the things that makes humans and animals special is our ability not just to be smart, but to adapt. So we can make complex machines like cell phones and international space stations, but it's very hard to build adaptive machines that change what they do as the circumstances around them change.
All right, so you mentioned computers. What is the difference between the computer that many of us have on our desk and the kind of machine intelligence that you're working on?
Sure. The big difference is opening up the world for robots. So machines, the beginnings of AI was getting machines to play games, for example. So we got computers that could master checkers in the 80s, chess in the 90s, and just last year, we have machines that can now play a pretty good game of Go. But if you think about any of those games, there's only a certain number of options at any given time, 8 or 10 or 12 things that you can do. The minute you're a robot in the real world or a human in the real world, there's an infinite number of things you could do at any given point in time, and that is a really difficult thing for a machine to do. They're sort of paralyzed by choice. So the work we do in my lab is trying to get robots to be able to adapt, to choose what to do next without us explicitly telling them what to do.
Okay, so what are they good at now? What are they not good at now, robots?
So they're very good at doing the same thing over and over again. So we have industrial machines. We're now just starting to see autonomous cars. This is obviously a big, big, big deal.
Yeah.
Part of the reasons why autonomous cars are starting to enter our world is, again, they still do only a few things. Speed up, slow down, turn left, turn right. They make that decision at a millisecond by millisecond time scale, but there's still a few things that they can do. And we're starting to deploy them in relatively simple environments. So in Western Europe, they're starting to deploy autonomous trucks for long-distance hauling. And they're creating regulation to go along with those autonomous trucks where they demarcate one lane on the highway that is for machines only, no people. So in the same way that we created factories and sort of said, okay, the machines can work in this area, make sure people stay out of their way, kind of doing the same thing with roadways. So it's an interesting issue because it started with a technical issue. How do we get machines to think for themselves? But it becomes also a societal and a policy issue. How are we going to decide about where robots can go and where they can't go?
Wow. Okay, so in 2011, we spoke with you after you received the President's Early Career Award for Scientists and Engineers. And just recap what you were working on then that garnered you that award.
Sure. So I was very honored to meet then President Obama at the White House, along with some other junior scientists working on different kinds of things. In my case, it's robots. And we were working on a particular robot at that point that was adaptive in the sense that when something went wrong with that machine, it was a four-legged machine. One of my students nicknamed it the evil starfish. And if you pulled a leg off the evil starfish, it didn't know what happened, but it would be able to eventually figure it out and keep going. So insert Terminator references here. So we're creating these adaptive machines that could recover from unanticipated situations like damage. And the way that we got them to do that was to create, in essence, a robot that could dream. So you mentioned physical simulation at the beginning of this segment. Basically, what this robot has is like a virtual world or a video game running inside its head, and it creates simulations of itself, little virtual versions of itself, and it thinks to itself, what would happen if I do this? What would happen if I did that? Thinks about things and then tries them out in reality. Things that work, it continues doing. Things that don't work, it goes back to the drawing board, so to speak, and thinks up new things to try.
And it was like Star Trek meeting Darwin. I mean, it was evolution in a cyber world, right?
That's it. So that's the other piece of the experiment. We have this virtual world where the robot can think, and it's basically running what's called an evolutionary simulation. It dreams up not just one scenario, but many scenarios. And those scenarios that meet with reality, that are more accurate than others, the robot keeps those, deletes the ones that don't do a good job of reproducing reality, and creates modified copies of the ones that survive. So it's breeding basically ideas. It's got an evolutionary process running in its head. And this is what's known as evolutionary robotics. So instead of creating robots or programming them by hand, get them or us to evolve robots to do something useful for us.
We do have a picture of the evil starfish that you mentioned on our webpage at vpr.net. Now, at the time, you received $500,000 for your research. I don't want to be like an accountant, but how was that money used?
That's a very good question.
I'm not your CPA, but
for the exactly. So we took that money and we continued on from the evil starfish, and we took this idea of evolutionary robotics, where we're evolving robots to do something useful, and we've been adapting it since that time to address this issue of AI safety. So we are now able to we're starting to make machines that are autonomous and that are driving on our roads. There are small robots in San Francisco that are rolling down the sidewalks, delivering fast food to people. The robots are coming. So the big question now is, how do we make sure that those machines are going to be safe?
Did you make advancements?
We're working on it. We have a project going on now in the lab called Twitch Plays Robotics, and this is actually a website that you can visit. If you Google Twitch Plays Robotics, you can try it out for yourself. And this is, in essence, a school for robots. So on the website, you'll see a whole bunch of these virtual robots that are evolving in a virtual simulation. And the people that arrive at the website are the teachers. And the idea here is that people get together and decide what they want to teach the robots. So people come up with the curriculum, so to speak, for the robots. And then once they issue a command to the robots, what they want the robots to learn, then they start to teach the robots. Yes, you did the right thing. No, you didn't. And the robots listen and get better and better at understanding the curriculum, being able to figure out how to obey what people on the website have asked them to do.
Josh Bongard, I can imagine, you must think something, and then you're the one person in the world who can think something that I can go into the lab and make this happen. I can create this goofy thing tomorrow.
Well, that's one of the great things about being a professor. If we're lucky, we get a little bit of funding and some bright students to work with us and try things out that may someday become a useful technology.
And what else is your team working on at the Morphology, Evolution, and Cognition Lab? Is there a shorter way? Is it like Moevco?
It's the MEC Lab.
Okay.
The MEC Lab. Right. That's much less of a mouthful.
Yeah,
absolutely. So I was telling you about TPR, Twitch Plays Robotics, our robot school. That's an attempt to make safe robots. We also work in another area called soft robotics. So at the moment, most of you are familiar with these rigid machines that are clunking down the hallway, or autonomous cars. They're made out of metal. They're very rigid. Those machines, obviously, from a physical point of view, can be unsafe to be around humans. So there's a move now to build soft robots. These are robots that are made out of exotic materials like metal foams and plastic and Play-Doh and all sorts of interesting materials, so that they're literally soft and can move into areas that would be difficult or impossible for a rigid robot to get into.
Okay, and tell me the application, dream it.
So the big application at the moment is medical applications. There's a lot of work on what's known as intelligent drug design. So in the not too distant future, you may swallow a pill, and inside that pill is a small, soft robot that then looks for example, a cancerous tumor in the body and swims upstream to find that tumor and delivers the drug exactly where it needs to go. So science fiction, but again, it's not too far off.
Okay. In 2016, you wrote, "The human species has recently painted itself into a corner and seems unlikely to find a way out with biological smarts alone. We're going to need help, machine help." So flesh that out a bit and explain what you mean and why machine help is going to save us.
Oh, that's a good point. So this is another aspect of...
Well, you made it, so...
I did.
Yes.
I did. This is another aspect of AI safety. So what can these machines do for us? They might be able to help us physically repair bridges or deliver drugs, but they might also be able to help us intellectually. So as we all know, our world is getting increasingly complicated. There are more and more decisions that our policymakers need to make, that we need to make on a daily basis. Our world is just getting more complex. And this is definitely not the world that our ancestors evolved into. So it's becoming increasingly difficult for one person or a few people to get together and make the right decision given how fast things are changing. So perhaps one application of machines might be robot advisors that can actually deal with all the data flooding in from various aspects of our world and help us make better decisions. They might be able to see more than we can, but hopefully they would leave it up to us to decide what to do with all that information.
Today, we're speaking with Josh Bongard. He runs UVM's Morphology, Evolution, and Cognition Lab. His research centers on evolutionary robotics, evolutionary computation, and physical simulation. We're learning about where robotics research and development is today, and hopefully being reassured that a robot uprising can't ever occur. Josh, cold, emotionless robots are a trope of science fiction. You've written that you think machine intelligence can actually help humans develop empathy. How would that work?
So that's taking the opposite view of Hollywood and a lot of popular media, as you mentioned, where we have these evil machines. They're somehow bent on getting rid of us or replacing us in some way. But it's really up to us to program these machines and direct them in terms of empathy and morality. Now, how would you ever create a moral machine? We were talking earlier about adaptive machines that decide what to do in what situation. We were talking about safe machines that would somehow do what humans would like them to do. So a moral machine is one that understands people. What do we prefer? What would we like our world to look like next year or 5 years from now? And be able to think ahead and work with us towards those common goals.
It's possible?
I hope so. I mentioned just before the break TPR, the School for Robots. So one of the things that these robots learn is not just to obey people when they ask the robots to do something, but they are also learning to predict beforehand how people are going to respond. So let me paint a bit of a picture for you here. On this website, Twitch Plays Robotics, you have a bunch of these virtual robots running around, and someone might come to the website and ask the robot, I want you to go pick up the red object. The robot hears that command. It's got a piece of language now. It's got a command from the user. It tries to do something. Maybe it walks towards the red object, tries to pick it up, but fumbles and drops the object. The robot is able to predict beforehand that the human is about to give it a thumbs down. It knows that it's failed to do what the person has asked. So not only does the robot understand what it was asked to do, but it understands the intent behind it. So it understands not just what it was asked to do, but what people meant by that command. And that's the beginning of empathy or morality, understanding other humans and what they might like and what they might not like.
Are we really close to artificial intelligence, to AI?
So how close we are, again, that's a tricky question, because what do we actually mean by artificial intelligence? And this is something I talk about with my students in the classroom at UVM. If you think about the word intelligence, it's very difficult to define exactly what we mean by that. Is a computer that can play checkers or chess or Go, is that intelligent? Is an autonomous car intelligent? What exactly do we mean by that? For most people these days, they mean human-level intelligence, a machine that can do one thing well, something else well. It has sort of the generality. It's able to do lots of things well like people.
All right, let's take a call now. We have Professor Mish Kabay, who teaches at Norwich University.
Great.
Professor Kabay, nice for you to call in and join us. What would you like to talk about? Yeah, hi.
Hi there.
Very much enjoying the show. I teach a course called Politics of Cyberspace at Norwich, and one of our topics is AI, and related is robotics. Professor, could you look at the issue of chaotic systems in neural networks, by which I mean systems that have unpredictable solutions, some of which are not comprehensible by the human beings, at least not at first. There's a famous case in 1988 where a neural network designed a circuit, and nobody could understand why it worked until they figured out that it was using inductance of nearby channels for the electrons, but nobody had thought of doing that. So I will stop the call and listen with great interest.
That's a great question. Thank you very much. I know the experiment you're talking about, and for our listeners, that was a very exciting experiment at the time, because as you mentioned, the computer was able to create a circuit for us, an electronic circuit in which an electrical engineer, a human electrical engineer, could not understand the circuit. So this is in one way exciting and also somewhat scary. And the other way is what these machines don't necessarily think like we do. They don't make like we do. As you said, they created different kinds of circuits that a human engineer can't understand. So what does that mean for the future of AI? And should we allow AI, which thinks differently and acts differently from people, to work alongside us? My opinion on that is it's perfectly fine as long as the machines understand people, as we were just talking about. Even if the robot knows how to make this circuit, even if it knows that people won't understand it, it has to know the third part, which is to know that even though people don't understand it, they're okay with it. If they're not okay with it, then the machine should not be making that circuit in the first place. So I think it's okay if we have machines that make things or do things that we don't understand, as long as they know before they do it that humans as a whole are going to approve of that action.
Will the machines ever be as smart as or smarter than people?
I don't see why not. Again, it's an uncomfortable thought for a lot of people. What will it mean when we have human-level intelligence? A lot of people feel that, again, this idea of us and them is maybe not the way things are going to go. Most of us carry around a cell phone in our pocket. If you look around, you can see more and more mergings between humans and machines. So maybe it won't be an us and them situation. There's a new technology on the way called brain-computer interaction, or BCI, and these are special electronic circuits that can interface directly with the nervous system, and it allows people that, for example, have locked-in syndrome to be able to move machines just by thinking about them. So we already have real-world cyborgs and a melding of machines and people.
Let's take another call. We've got Bob calling from Winooski. Hi, Bob. Thanks for calling today.
Well, thank you for inviting me. I have a question based on Isaac Asimov's 3 laws that he wrote about in iRobot. Are there any kind of ways that we can have international agreements or something that say you may not this robot it may not harm people, humans?
And to go a little further on the safety, we had an email from Dennis in Burlington. He says, how do we prevent another HAL from 2001 A Space Odyssey or Cyber Rebellion? And when he says another Cyber Rebellion, I can't remember the first one. I hope there wasn't one. But how these are great questions.
They are great questions. And thanks for your question, Bob. So that's a very good question. And policymakers are now starting to get into the game. So now that AI is invading our everyday lives, policymakers are starting to ask the question about how would we actually regulate these machines? How would we regulate against HAL or regulate some form of morality like Asimov's 3 laws? There's now an annual meeting at the United Nations in Geneva, Switzerland, around the idea of lethal autonomous weapon systems or laws, more popularly known as killer robots. So the UN and other international legislative bodies are starting to think about how to actually legislate against such machines. It's a difficult thing to do for the simple reason that we don't have anything to measure. If you think about legislation, for example, about cars, we have a measurement, miles per gallon. So cars below a certain MPG are going to be taken off the roads and vice versa. In terms of nuclear safety, there is millisieverts. So humans that receive more than a certain amount of millisieverts, they were in an unsafe situation from a policy point of view. So one of the challenges for us scientists who work in robotics and AI is coming up with something to measure. And once we have something to measure, then society as a whole can decide what is the maximum level of intelligence or free will we might allow in machines. So that's the big challenge at the moment, is what exactly we're going to measure and then legislate around.
We've got another interesting question from Stacy. She's calling from Morrisville. Stacy, thanks for joining us today. What's your question?
I wanted to ask, what happens if someone without good intentions tells the robot to do something?
That's a great question, Stacy. So what if a bad actor, for example, tries to teach robots to do something that the rest of us might not be huge fans of? That's a good question, and I don't have a good answer for you about that because we're now talking about technologies that involve people and machines. I can tell you that on Twitch Plays Robotics, the school for robots that we run on the web, we do see bad actors. We see bad guys and girls coming in and getting together and deciding that they want to teach the robots a very bad word. And after a while, you'll see the good guys and girls realize what's happening, get together, and work against this small group of bad actors. So at least in this small example we have on the web, our hope is that the good guys and girls outnumber the bad guys and girls.
We can only hope.
We can only hope.
In your evolving robots work, you actually are using outside human interaction to help robots develop the right way or the wrong way to do things. So explain that.
Sure, I can explain that in a little more detail. So what happens in that case is we're trying to create machines that can understand language. So we want to have people be able to tell their robot what to do. So the robots have to take in language, and then they have to consider an action. What are they going to try and do to obey that command. So if the command is shovel the front drive and they shovel the lawn instead of the drive, that's an action. And then the third part is they need to, again, understand people. So at the moment, machines, unfortunately, are like sociopaths and psychopaths. They don't understand other people. They don't understand that people have an inner life. They have preferences. They have pleasures. They have pains. They just aren't able to predict or understand people. So that third part is really important, is that the robot needs to take in the command, consider an action before carrying it out in reality. It's got this virtual world running in its head where it tries out ideas and broadcasts that to people. In essence, the robot is saying, what do you think about this? Will this do what you asked me to do? And the robot needs to be able to predict before the human responds. The robot needs to say, I'm pretty sure that you're going to like this idea. If a machine can't do that, if it's not able to understand people and predict what they will and won't like, we don't have safe machines.
So you have people interacting. They're giving a thumbs up or thumbs down to the action. Kind of explain how that works.
Yeah, so on this TPR website, people can watch robots in real time, and then there's a chat window where they type in commands like move or go pick up the block or shovel the drive. And then once the robots hear that command, the users on the website are watching these virtual robots jumping around, and as you say, they give a thumbs up if the robot is doing what they asked it to do, or thumbs down when it's not doing what it wanted to do. And the robots are collecting all of that data from the humans, data from the actions that they're performing. They remember their own experiences and the language that they received, and they tie those three things together: language, action, and social response using machine learning and AI. They learn the common patterns among those three things, and that allows them, once they get a new command to do something new in a new situation, they're able to come up with an action that people approve of before the robots receive the response from people.
So they do retain that.
In simple settings. So again, this is basic research. This is still in the lab. This is not something that we're going to be deploying in real robots anytime soon, but trying to understand how machines do that and trying to understand how people do that is really important.
Let's take another call. We've got Charlie calling from Franconia, New Hampshire. Charlie, thanks for joining us today. What's your question or comment?
Hey, guys. Thanks for taking my call. So I'm wondering if from what I understand, AI is really good at doing one thing really well, language recognition or movement or image analysis or, one task. And I'm wondering if one of those tasks could be choosing which of the other tasks to implement in a given situation. So, like, if the AI can have a layer of control that allows it to intelligently decide what it needs to implement in the collection of all of the things that AI already are capable of doing to accomplish a given task.
So that's a really great question. Yeah. So if I understood your question right, you pointed out a big challenge in the field, which is known as catastrophic forgetting. So at the moment, even with state-of-the-art machines, when they learn task one and then they attempt to learn task two as well, as they learn task two, they forget task one. It's very difficult for them to hold on the ability to succeed in both environments. That's catastrophic forgetting. And if I understood, again, your point, you raise an interesting way of addressing that challenge, which is to have some sort of top level that's able to pick and choose among these individual capabilities of the machine. We have some openings in my lab. If you're interested in applying for a grad student position, you sound like exactly the kind of people we're looking for. Great question.
So, Josh, if the robots are relying on human input to figure out how to do things, does that mean that they really aren't autonomous? And is the idea to make them autonomous at some point?
That's, again, a great question. It takes us now into the realm of philosophy. What does it mean to be completely autonomous? Humans are not completely autonomous as well. We're parts of communities and societies and nations. We rely on each other, and most of us care about what others think about our actions and the choices that we make. So no, these robots are not completely autonomous. They're relying on people to learn and get better at what we want them to do, but they're non-autonomous in a similar way that humans are non-autonomous. We rely on our parents and our teachers and our friends to learn about the world around us, and importantly, to learn about the social world around us.
You mentioned something earlier that you want robots to be able to dream. So explain that to me, because that one I don't get.
Okay, so that's back to the evil starfish. This was a project we worked on a few years ago where we have this physical four-legged robot that looks like a cross between a spider and a starfish running around. And as it's running around, it's running basically a video game in its head. It's got one of these virtual worlds. And inside that virtual world is a virtual evil starfish. It thinks up a copy of itself. Now, it turns out that robots don't really sleep, so it's dreaming all the time. And as it's dreaming all the time, it's using those dreams to learn about what people just told it to do, or it's thinking about things it might do in the next millisecond or the next hour. It's dreaming while it's awake. And interestingly, neuroscience tells us that we also do the same thing. We also are dreaming or predicting as we move around in our daily lives. So again, an interesting connection between robots and people.
All right. You have done a great job of telling us where we've come from, where we are now. What do you think robots will be able to do in 20 years that they can't now?
I think what we're going to see is, again, large numbers of robots working together. So some of you might have seen the opening ceremonies for the Winter Olympics, in which there were 1,000 drones creating these beautiful patterns in the air. One of the things that machines can do well, and people can sometimes do well, which is work together in large groups. So I think there are some big challenges we face in terms of rebuilding infrastructure in the United States. This is going to require a lot of people power, or alternatively a lot of machine power. So I think large numbers of machines working together to do large-scale things for us, that's going to be part of the robot future.
I do want to mention one more thing. We're almost out of time, but I think people can kind of follow your class or take your class on a subreddit group. Is that right?
Yeah, I run an online course through Reddit called Ludobots, Ludobots. Ludo is Latin for play. So come join us on our online course and play and build robots along with us.
Josh Bongard runs UVM's Morphology, Evolution, and Cognition Lab, where his research centers on evolutionary robotics, evolutionary computation, and physical simulation. Thank you so much for sharing your research with us today, Josh.
My pleasure, Rick, and thanks for all the great questions.